effect of pH of the medium on the solubility of sparingly soluble salts. Now, sparingly soluble salts with anions, fluoride, carbonate, sulfide, acetate, benzoate. The solubility of sparingly soluble salts with anions like fluoride, carbonate, sulfide, acetate, benzoate, etc. The solubility increases in acidic solution, acidic medium, than in water. Can you give some examples of salts with these anions? SrF2, CaF2, BaF2 in the first case, silver carbonate, barium carbonate, calcium carbonate in the second case, silver sulfide, MnS, silver acetate, silver benzoate. These are some of these salts which are sparingly soluble salt with these anions. Anions like fluoride, carbonate, sulfide, acetate, benzoate, etc. For such salt, the solubility is increased in an acidic medium than in water. The solubility of salts, sparingly soluble salts, with anions like chloride, sulfate. You can include here chromate also, CrO4 2-, like lead chromate, barium chromate. The solubility of sparingly soluble salts with anions like chloride, sulfate, etc. Example, lead chloride, lead sulfate, barium sulfate. The solubility is not affected by the presence of acidic solution. The solubility is not affected by adding H+. So it is not a universal factor. Common ion is a universal factor. Diverse ion is a universal factor. Temperature is a universal factor. Complexation is a universal factor. This does not affect the solubility of all sparingly soluble salts in the same way. These set of salts with anions like fluoride, carbonate, sulfide, acetate, benzoate, chromate, etc. The solubility is more in acidic medium than in water. The salts like lead chloride, we are not bothered about sodium chloride because anyway it is soluble. We are talking about the whole thing is about sparingly soluble salt. Take sparingly soluble salts like lead chloride. First group of cation analysis, lead is precipitated as lead chloride, white precipitate, right? It is soluble in hot water. Lead sulfate, barium sulfate. For these salts, the solubility is unaffected by the presence of acidic solution. Why this difference? What is the role of H+ to these salts? Why not it gets unaffected here? First you note it down and then we will see how we can qualitatively explain and then how we quantify the result. You understand what I mean? Why these, for these salts with these anion, the solubility is increased in a given acidic medium. Why not in this case? That means what? This particular factor is not a common feature for all sparingly soluble salts. It depends on what is happening when you add an acid. Suppose I take any one salt in this list, barium fluoride. Right? To this I add a few drops of HNO3 or HCl. I should not add HF. Why? HF will provide a common ion. I should add an acid which is not providing any common ion. Let me add HCl. HCl aqueous. What will happen? It will dissociate fully, forming H plus plus Cl minus. What will H plus do? It will remove fluoride ion. H plus will tag, which will remove fluoride ion, forming more and more HF. So what is Le Chatelier-Brown principle say? If you remove one of the products from equilibrium, it will favor the forward reaction. What does it mean? The solubility is increased. You understand? It is equivalent to removing fluoride ion, so the equilibrium is shifted from left to right, which means what? The solubility of barium fluoride in a given acidic solution is more than the solubility of barium fluoride in water. Why? What does it do? The added H plus added H plus combines with fluoride ion to form a weak acid HF. You know HF is a weak acid because it is hydrogen bonded. Correct? HCl is a stronger acid. HI is a stronger acid, but HF is a weaker acid because HF is associated through intermolecular hydrogen bonding. So the equilibrium, you are trying to remove fluoride ion, and it forms corresponding weak acid, H2CO3, H2S, acetic acid, benzoic acid. All these are in acidic medium, they form the corresponding weak acids, so that the solubility equilibrium is shifted from left to right. You understand what I mean? In a given acidic solution, the anions react with H plus to form the corresponding weak acid HF here. It may form either bicarbonate ion or H2CO3. Either it may form HS minus or H2S. Here it will form acetic acid. Here it will form benzoic acid. Correct? With the result, what happens? The solubility equilibrium is shifted from left to right. And let me take one more case. Take silver benzoate. Take another example in this list, silver benzoate, C6H5 COOAg, which dissociates in water to form Ag plus plus benzoate ion. Silver benzoate. Right. I am adding a salt, like HNO3. I am avoiding HCl. Why? The HCl will form a precipitate here. Correct? So HNO3 will dissociate to form H plus plus NO3 minus. What will happen? The added H plus will remove benzoate ion, forming benzoic acid, which is a weak acid. The added H plus combines with benzoate ion to form benzoic acid, which is a weak acid. So the solubility equilibrium is which is the solubility equilibrium? This one. The solubility equilibrium is shifted from left to right. in acidic solution. Correct? What does it mean? So there is increase in solubility. This is the quantitative aspect. Why it has no effect on the solubility of lead chloride? Why it does not have effect on the solubility of barium sulfate, lead sulfate? Because it doesn't form a weak acid. You understand? Let us take the case of lead chloride. Here I should not add HCl, I should add HNO3. Why? If I add HCl, I am providing a common ion effect. So, lead chloride is in equilibrium with Pb2 plus 2Cl minus. I add HNO3. What is the result? H plus will react with Cl minus, but again it will remain as only H plus and Cl minus. It is not virtually removing chloride ion because HCl exists there. In all the other cases, what happens? HF is formed. Benzoic acid is formed. Acetic acid is formed. Effectively, the anion is removed. Here the anion is still there. Why? Because you don't have a weak acid. You form a strong acid which exists as H plus and Cl minus. I hope you understand. So here the solubility is practically unaffected because of what? The HCl is not a weak acid, it is a strong acid. So it remains as H plus and Cl minus. Earlier case, why the solubility was affected? Because you are H plus removes fluoride ion, H plus removes benzoate ion, H plus removes acetate ion from the equilibrium system. If you are removing one of the products from equilibrium system, it will favor that direction. Here you are not removing it, it remains H plus Cl minus forever. So it is not removing Cl minus from it because H plus and Cl minus will remain. It is not forming a. What is important here? The anion which we have listed reacts with H plus to form weak acid. That is why the solubility is affected. Is that clear? That is a qualitative aspect. How do you quantify the result? Take a problem in this. Solubility of SrF2. Calculate the solubility of strontium fluoride. Calculate the solubility of strontium fluoride in moles per liter. Calculate the solubility of strontium fluoride in moles per liter in 1 liter of pH 4 solution. In 1 liter of pH 4 solution. That means what? You are adding an H plus. Given KSP of strontium fluoride, is 2.8 into 10 power minus 9. KSP is 2.8 into 10 power minus 9 for strontium fluoride. Ka for HF is 6.76 into 10 power minus 4. And what you are adding? Correct? pH 4 means what? 10 power minus 1 liter of. So pH 10 power minus 4 molar H plus is added to SrF2. Right? Now, let F is the fraction of the total fluoride. Which remains as free fluoride ion in acidic solution. Let me denote small f as the fraction of the total fluoride which continues to remain as free fluoride ion in an acidic solution. What are the two ways in which fluoride ion can exist? What are the two ways in which the fluoride ion can exist? One, as free fluoride ion. Other one, as HF. Correct? You are adding H plus. Part of it goes into forming HF. Part of it remains as free fluoride ion. You need free fluoride ion for solubility. If all are remaining as HF, the problem is closed. You understand? So, total fluoride ion, part of it is remain as free F minus, part of it combines with H plus added to form HF. If I represent small f as the fraction of the total fluoride ion which continues to remain as free fluoride ion in a given acidic medium, how do you express that F minus, that F? Tell me. What is that F? Don't be, if you want, if to avoid any confusion, you take it as instead of F, X also. Because here is F, here is F. So this fraction is what? Concentration of free fluoride ion divided by concentration of free fluoride ion plus concentration of HF, correct? Yes or no? There are two ways in which fluoride exists. What is the fraction of the fluoride ion which reminds us this is what? This is free fluoride ion, correct? What I mean by F minus is free fluoride ion. F minus concentration by total. Correct? This you try to simplify using the Ka expression. What is Ka for HF? What is Ka for HF? Come on. No, I am not asking the value, man. What is the equation? H3O plus into F minus divided by HF. So, what is this fraction? Both numerator and denominator divide by F minus. What will you get? 1 by 1 plus HF by F minus. Simplify HF by F minus from here. From this HF by F minus is what? From this. Bring HF that side. S3O plus by Ka. Substitute that S3O plus by Ka here and rewrite it. Therefore, this becomes what? F is equal to 1 by 1 plus H3O plus by Ka. What is this? Ka by Ka plus H3O plus. Correct? You understand? Simplify this. You get Ka by Ka plus H3O plus. What is Ka given? 6.76 into 10 power minus 4 divided by 6.76 into 10 power minus 4 plus 10 power minus 4. Take 10 power minus 4 out and cancel it. What do you get? 6.76 by 7.76, which is obviously a fraction. It cannot be equal to 1, it cannot be greater than 1. Out of the total fluoride, the effective fraction of fluoride ion which continues to remain as free fluoride ion in a given acidic medium, in this case is 6.76 by 7.76. Okay, you write the solubility equilibrium SrF2 giving SR2 plus 2F minus. Let S dash be the solubility of SrF2 in acidic medium. What is asked is S dash. So what is the effective concentration of SR2 plus at equilibrium S dash? What is the effective concentration of fluoride ion? 2s dash into F. Why? This is S dash. Normally it is S, this is 2S in water. Here it is S dash. This will be 2S dash into the fraction. Suppose the fraction is 1. What does it mean? No acid is there. Everything is only water. Correct? So this effectively what happens because of this fraction F, the overall F minus is reduced. Substitute that in the KSP expression and calculate F you know. Can I rub up this? The last value alone you need. That is, the fraction is what? 6.76 by, what is this fraction? The fraction of the total fluoride which continues to remain as free fluoride ion in a given acidic medium. Okay, now substitute in the KSP expression, KSP equal to, what is the KSP value given? 2.8 into 10 power minus 9 equal to concentration of SR2 plus into concentration of F minus squared. What is this? S dash into 2S dash F squared, which will be how much? 4 S dash cube F squared equal to KSP. Correct? You cannot neglect anything here because everything is a product. What do you know? You know KSP, you know 4, you know F. So you know F value, you know KSP. What is the only unknown? S dash. I will give you the value of S dash, you check it up later. 9.7 into 10 power minus 4. S dash is 9.7 into 10 power minus 4 molar. So what is the conclusion? The solubility of SrF2 in 1 liter of pH 4 solution is S dash, which is equal to 9.7 into 10 power minus 4 molar. What you observed? What you observed in the beginning of this particular subtopic? Solubility is more. Calculate the solubility of SrF2 in pure water. In water alone, what is it? How do you calculate it? KSP equal to 4S cube. Correct? 4S cube is 2.8 into 10 power minus 9. Why 4S cube? 1:2 type of salt. Calculate S. The solubility in water. S is cube root of 2.8 into 10 power minus 9 divided by 4. If you simplify, you will get 3.4 into 10 power minus 4, which you check it up. So what do you find? Roughly 3 times, nearly. So what is the conclusion here? S dash is greater than S. S dash is in H plus. S is in water. So what is the conclusion? The solubility of this salt. What is the speciality of this salt? This salt contains fluoride ion, which in acidic medium forms a weak acid HF, so that the equilibrium is shifted from left to right. You understand? See, the qualitative conclusion is the solubility in an acidic medium for such salts is, suppose it is given as a statement, solubility of all sparingly soluble salts in a given acidic solution is greater than that in water, it is false. Solubility of sparingly soluble salts whose anions in an acidic medium forms weak acid, for such salts the solubility is increased. I given you a few examples: SrF2, BaF2, CaF2, barium carbonate, calcium carbonate, strontium carbonate. Then cadmium sulfide, all sulfides, salts, chromates, acetates, benzoates. Is that clear? Okay. So, summarizing all the factors quickly. In the presence of common ion, solubility of a sparingly soluble salt is lowered because it affects the equilibrium. Then, diverse ion, solubility is increased because the activity term gets modified. That electrolyte which you add is called an indifferent strong electrolyte. Indifferent electrolyte. Why do you call it indifferent? No common ion, no common cation, no common anion. Third, temperature. If delta H0 solution process for the salt in water is positive, KSP at higher temperature is greater. If KSP at higher temperature is greater, solubility is greater. Correct? Solubility is increased if delta H0 is positive. Next one. Effect of a suitable complex ligand which forms a soluble complex ion. The solubility in such cases is much more than that in water. For example, cyanide ion, ammonia, methylamine, thiosulfate ion. These forms soluble complex ion with the suitable metal which is form of a precipitate. So it dissolves. So the solubility is more in a given ligand than in water. The last one, pH. pH is not an universal factor. It affects the solubility of only certain salts. Fractional or selective precipitation. A solution contains 0.01 molar each of thallium ion, Pb2 plus Ag plus. That means you have a beaker containing all the three cations together in the mixture. Each one concentration is 0.01 molar. Chloride ion is added drop by drop. Chloride ion is added drop by drop. What is the order of precipitation? What is the order of precipitation? What percentage of each ion? What percentage of each ion already precipitated when the next ion begins to precipitate? What percentage of each ion that is already precipitated when the next ion begins to precipitate? KSP of thallium chloride, lead chloride, silver chloride are 3.5 into 10 power minus 4, 1.6 into 10 power minus 5, 1.8 into 10 power minus 10 respectively. What do you mean by selective or fractional precipitation? What you are having here, you have a solution which contains thallium ion plus Pb2 plus Ag plus 0.01 molar each. I am adding chloride ion drop by drop. Why should I ask drop by drop? Then only I can find out what is precipitate. If I add like this, all three will be precipitated in one shot. Suppose open the burette and see up. Right? Everything will be precipitated and the problem has no sense. Right? Now, use the KSP of thallium chloride and you have 0.01 molar thallium ion at equilibrium. What is the concentration of chloride ion for thallium chloride? 3.5 into 10 power minus 2, correct? How? How? KSP divided by the metal ion concentration, yes or no? KSP of thallium chloride is what? Write the expression. KSP of thallium chloride is concentration of thallium ion into concentration of chloride ion. KSP of lead chloride is concentration of Pb2 plus into concentration of chloride ion squared. KSP of silver chloride is concentration of Ag plus into concentration of Cl minus. First to find out what should be the equilibrium concentration of chloride ion from thallium chloride. Similarly, at equilibrium, what is the concentration of chloride ion for lead chloride? Root of KSP of lead chloride divided by 10 power minus 2, correct? I hope you understand. What is KSP of lead chloride? 1.6 into 10 power minus 5, 1.6 into 10 power minus 5 divided by 10 power minus 2 root. What will you get? 16 into 10 power minus 4 root. What is that? 4 into 10 power minus 2 molar, correct? Yes or no? Do the same thing for silver chloride. What is the concentration of chloride ion at equilibrium for silver chloride? KSP of silver chloride divided by 10 power minus 2. Why you take 10 power minus 2? Because that is the concentration given. Okay, what is that? 1.8 into 10 power minus 8 molar. So, the chloride ion concentration at equilibrium for silver chloride is this. The chloride ion concentration for thallium chloride at equilibrium is this. The chloride ion concentration for lead chloride at equilibrium is this. When will the respective cations get precipitated? When each chloride ion concentration exceeds more than that. Why? These are the equilibrium concentration. That means saturated solution. When the chloride ion concentration slightly exceeds this, what happens? Q greater than KSP. Correct? When chloride ion concentration is slightly more than this, the ionic product exceeds the solubility product for this. So, still you can compare the three concentration and decide. Each one should exceed slightly greater than, but the comparison is from the equilibrium concentration, which requires the lowest chloride ion concentration. So, silver chloride will start precipitating first. That is why you are adding drop by drop. When you add drop by drop and shake, you will observe silver chloride precipitation only. Then, next one out of the two, which is lower? Second, thallium chloride. The last is lead chloride. The order of precipitation is this. Why? Why? The one which requires the least concentration of chloride ion will get precipitated first, because in that case this Q greater than KSP is reached much earlier. That is why you are adding drop by drop. So the order of precipitation is silver chloride first. There will be no way by which lead chloride first, then thallium chloride, then silver chloride. That is against theory. That cannot happen. First, the order of precipitation is this. Okay. So when will silver chloride really start getting precipitated? See, you should understand this principle properly, because frequently objective questions are asked in this. When will silver chloride start getting precipitated? Come on. When the concentration of chloride ion is slightly more than this. Because at this point no precipitation. Why? Equilibrium. Silver chloride will start precipitation when chloride ion concentration exceeds 1.8 into 10 power minus 8 molar. Correct? If you keep on increasing it, what will happen? Silver chloride getting precipitated, getting precipitated, getting precipitated. Here begins one crystal, one microcrystal goes on forming. Then, when will thallium chloride begins to precipitate? This is the first one. Thallium chloride starts to precipitate when concentration of chloride ion is slightly greater than, what is the value? 3.5 into 10 power minus 2. Correct? Please note, it starts. Here also it starts. If you keep on adding more chloride ion, it will continue to precipitate. Then, thallium chloride begins to precipitate. You have finished silver chloride. You have to find out thallium chloride, when it starts getting precipitated, practically silver chloride should be out. Otherwise, there will be a mixture comedy. That is what is called fractional precipitation. When the second cation begins to precipitate, the first one should have been precipitated practically completely. That we have to examine. So, the thallium chloride starts to precipitate when chloride ion concentration exceeds 3.5 into 10 power minus 2 at this point. The concentration of Ag plus in solution not precipitated as silver chloride is what? No, you have to find out. Negligible you cannot say. You have to calculate it. What is it? Ksp of silver chloride divided by chloride ion concentration for the second one. Correct? What do you mean by 2? 2 is for the second one to get precipitated. What is that? Ksp is not changed. What is it? 1.8 into 10 power minus 10 divided by 3.5 into 10 power minus 2. The percentage of Ag plus remaining in solution not precipitated. The percentage of Ag plus remaining in solution not precipitated when thallium chloride begins to precipitate is what? 1.8 into 10 power minus 10 divided by 3.5 into 10 power minus 2 into 100 divided by 10 power minus 2. Why 10 power minus 2? That is the starting concentration. 0.1 or 0.01? 0.02. This will be taken from that into 100 because percentage divided by 10 power minus 2. Simplify and see how much you get. Simply see and how much you get. Approximately 5 into 10 power minus 5%. It is nothing. Approximately 5 into 10 power minus 5%. Right? What percentage is already precipitated? 99.9999 something. Very little. It is practically nothing. Because anyway 100% precipitation is not possible. Very little will remain unreacted. So, if it is approximately 99.9 or better 99, better 999, still better 999. Approximately you can take 99.9% is already precipitated. That means it is selective precipitation will be fantastic. If 99.9% is already precipitated when the second one begins to precipitate, what is the result? It is possible to control the precipitation. Selective means you are controlling. So if 99, so if the result is 100 minus this will be what? Close to this. So just make a note of it. If 99.99%, 99.999 or better accuracy 99, still better accuracy 999, still better accuracy 99999. So approximately 99.9% of the first ion is already precipitated when second ion begins to precipitate. Then what is the result? The selective or fractional precipitation will be successful. 99.9% of the first ion is already, it has been precipitated. When the second one, what is the second one? Thallium ion. What is the first one? How do you get this? 100 minus, this is in solution. 100 minus 5 into 10 power minus 5 is what? 99.999 something. Correct? So which is close to 99.9. If roughly you can take 99.9% of the first ion is already precipitated, it means what? Separation is possible by controlled precipitation. That controlled precipitation is what is called selective precipitation or fractional precipitation.